Hey everybody, we are continuing on with number 11 for our lecture series now, and that's talking about density curves and the normal distribution. And this idea about the normal distribution is going to be a super important key topic, so let's focus on the beginnings of it. Our EQ, what is the proportion, or what does the portion under a density curve actually tell you? Okay, so let's go ahead and figure out what is a density curve in the first place. Well, sometimes we have enough data in a distribution that an overall pattern becomes very regular and very obvious. And if that's the case, we can draw a smooth curve over it like we've done in the past, and we can use that as a model. So we transfer that data into this smooth curve and it becomes a density curve. Okay, because underneath that density curve is going to represent every single possible observation that your quantitative variable will take. So what that tells us, it describes the generic pattern of a distribution. And since it represents 100% of all of our individuals, then the area underneath that density curve is going to equal 1, or 100%. Moreover, the curve is always going to lie on or above the x-axis. So I've highlighted almost everything in this box because this identifies the two main identifiers and defines what a density curve really is. So we got to know these two things. This makes a legitimate density curve. All right, so let's talk about a couple other properties of density curves that are really important for us. The first one is we should be able to identify what is the center of a distribution from a density curve just by visual inspection, and that doesn't even matter what our shape is of this distribution. So a density curve really can be skewed, it can be symmetrical, unimodal, bimodal, it doesn't really matter. But we can still identify our measurement of center by just following a couple of key things. First of all, the median is the one that divides the curve in half. Now that's a little bit harder for us to see, but what it means is that 50% of all of our individuals will be to the left of that mark, and 50% will be all to the right of that mark. Okay. The other thing that we can look at is if all of this had some amount of weight to it, right? If this was a solid object, where would you balance it? If you had like a pencil that you were going to be balancing on, where would you actually balance this distribution with your pencil? And that actually would be at C, right? And that's going to be where the mean is located. Okay, then the next thing that we could look at, this one's easy by visual inspection. The mode is just your peak. It's just the highest point, so that's easy enough, and that's going to be A. So we had A is our mode, we had our median was at B, and then we had our mean at C. The next thing we can look at it too is the area underneath a region of a curve. This happens a lot, and this is actually a calculus idea of finding the area underneath a curve in some kind of bounded region. The cool thing is about statistics though is we found ways to do this without using calculus, and we'll see that in the next lesson. But this is a really powerful tool because what this will tell you, the area underneath the region of a curve is going to represent the percent of observations that are within that range of values. Okay, knowing those areas there is going to actually be really helpful, and you'll see why in the next part of our lecture today, and especially in the next lecture tomorrow. Okay, let's take a look at an example now with a density curve. So we can see that this density curve is somewhat skewed, right? We know the total area underneath the curve is 1, and we have an area of a shaded region. Let's answer some questions. Why is this a legitimate density curve? This is super simple then. We know that it has two different things that we need to pay attention to. First of all, is the area underneath the curve 1? And is it entirely on or above the x-axis? And we can put a check next to each one of those key ideas. Yes, the area underneath the curve is 1, it tells us so, and it's pretty clearly lying on or above the x-axis, so we're good there. It is a legitimate density curve. Now, what's the proportion or percentage of observations between 7 and 8? Well, that's just the area of that bounded shaded region. So that's 0.12 or 12%. And this might not make a lot of sense right now, but again, as we start to look at more and more examples, understanding these principles will make a ton of sense. All right, our next task is to move on to one of the more important concepts, and that is knowing this thing about the normal distribution. So normal distribution is a huge tool that we will use. The thing about the normal distribution is it is a density curve that is unimodal, symmetrical, and bell-shaped. More than that, it follows some very specific rules, and we will touch on those rules here in just a little bit. I'm going to zoom out just to give myself a little bit more room and make sure everything is visible. The normal distribution follows what's known as the empirical rule. So the empirical rule is also known as the 60, 68, 95, 99.7% rule. Now, let's see why. So, again, this is going to be something that is very special. It is unimodal, it is symmetrical, and it is bell-shaped, and it follows this empirical rule. Lots and lots of things will follow this particular distribution, or very close to it. You'll see in AP Stats a ton approximately normal distributions, and this is what we are talking about, this kind of curve. Okay? You're going to learn to draw it, you're going to learn to love it, you're going to learn to work with it. Let's get to it. So, one thing we notice, because it's symmetrical and it's unimodal, the mean and median are going to be the same. So the mean can be placed right there in the center. Okay, we know where the mean is. Now, what's special about this is we have these things here called inflection points. This is where the curve starts to change from being like concave to convex. And what this will do is it will mark one standard deviation away from the mean. So this is a positive standard deviation, it's above the mean, and then down here we have a standard deviation that's below the mean. So that's positive 1 sigma and negative 1 sigma. And what's super special about this is because it's a normal distribution, it follows this 68, 95, 99.7% rule. And what that tells me is that 68% of all of my observations are going to land within this particular region, within one standard deviation of the mean. 68% will lie within there. Okay, now one thing that you can do is imagine again, like if I were to pour salt out of a salt container, like just a big old Morton's jug of salt, and I just poured it against some kind of wall, it would form a nice mound like this, and it would look actually pretty symmetrical. You can try this yourself, just be prepared for a bit of a mess. Okay, what this will tell me is that where I have that inflection point, that concave to convex part, this mark right here, that marks one standard deviation for where the salt will lie. And what this tells me is that 68% of all of my granules of salt, approximately, roughly 68% of all of my grains of salt, will lie within one standard deviation of the mean. Okay? Not only that, but I can say that if my average grain of salt is going to be right there in the center, then from my center to one standard deviation, these are symmetrical to each other on either side of that distribution, which means I will have 34% of all of my granules of salt lying on either side of the mean within one standard deviation of it. Okay? Next thing we can do is we can look at this next mark. You'll notice that this mark is one standard deviation away from the mean, so is this one. So this next one would be 2 standard deviations away from the mean, and it's positive 2 standard deviations since it's above the mean. This one would be negative 2 standard deviations away from the mean. Since this is the 68, 95, 99.7% rule, what percent of our observations do you think will land within 2 standard deviations of the mean? You probably guessed it, it's going to be 95% of all of our observations are going to land within 2 standard deviations of the mean. Okay? Within 2 standard deviations of the mean. And that's actually going to be really helpful for us too, because then we can start to figure out, well, how much are going to be in these shaded regions that I'm making here between 1 and 2 standard deviations from the mean. It's just a little bit of clever subtraction, right? We've already accounted, we know that that's 95% is within 2 standard deviations away from the mean, but if we take away the amount that's already been accounted for, 68, we're left with 27%, right? And if we're within 27% of 27% is left over, we've got it among 2 different regions. 27% divided by 2 is going to give me 13.5%. So that tells me that 13.5% will be in this shaded region of any approximately normal distribution. We'll have 13.5% of our observations between these 2 marks, 1 standard deviation and 2 standard deviations away from the mean. Now, let's find out what's special about the 3rd mark. Well, as you probably guessed by now, this is 3 standard deviations away from the mean. And since it's the 68, 95, 99.7% rule, we have 99.7% of all of our observations will lie within 3 standard deviations of an approximately normal distribution's mean. Okay? This is almost 100%. It's so close. So almost 100% of all of our observations in a normal distribution will be within 3 standard deviations from the mean. And that's a really helpful idea that's going to help us start to identify certain key features of normal distributions when we maybe only know the minimum and maximum. We're going to be able to start to figure a few of these things out. Okay? So what are each of these pieces of information? Well, now we can do the same tact that we did before by looking at, if I've accounted for now 99.7% of all observations, and I've already accounted for 95% of them, that means I have 4.7% left for these 2 shaded regions. But I've got 4.7% divided by 2, and that's going to give me 2.35%. So 2.35% of all observations will be within this shaded region. Now our last region seems like it's inconsequential, but there is a super tiny little region here that we can address. So here we would say this little chunk has only 0.03% left over because we've already accounted for 99.7% of all of our data at this point, or all of our individuals in distribution. So that means we have 0.3% or 0.15% on either side here if we are looking at it in terms of divided equally between 2 different chunks. This is what's known as the empirical rule, looking at this normal distribution and dividing them up into these different chunks. And dividing these up into different chunks, we can start to answer all kinds of really good questions and get really good information from just basic data about a normal distribution. And you'll see that in our examples. So what I want you to do next is take a look at the questions that are the topics I'm going to write down in just a second here on the screen, and make sure you have these written down. You 100% should have drawn this on your paper, copied everything down, colored it in, treat yourself to a little bit of crayon therapy, and then write down the rules that I'm about to do here. Okay? Alright, so here's the last bit that you need to make sure you have written down. The empirical rule, by definition, for all normal distributions says that 68% of all observations are within 1 sigma of mu, 1 standard deviation of the mean. 95% of all observations are within 2 sigma of mu, and 99.7% of all observations are within 3 sigma of mu. Can't tell you again how useful this rule is. It's what defines a normal distribution. This only works, this is only applied to normal distributions, but we find naturally occurring phenomena that follow this normal distribution so often that this rule is used a ton. So make sure you've got this written down on your own sheet of paper. I don't care if you copied it straight from me. I don't care if you did it all on your own. I don't care how beautiful you made it, but make it good and make sure you can have access to this to use it again. You will definitely want it on your examples and assignment. Thanks for watching, you guys. Have a wonderful day, and I will see you next time.